Thank you very much, Tom, for inviting me again to the Landsberg seminar. So I've been here last year already. And last year, I mostly spoke about this part here. So about how to understand the reasons for the high open circuit voltages. And I'll say a few words on that at the end of my talk. But this year, I wanted to dedicate to the experimental realization of high open circuit voltages. So last year, in the lab, we just tried to make solar cells with as high open circuit voltages as possible. Yeah, that was just the task. And I'll just tell you how it went. And then we'll see what we learned from that. Yeah. And essentially, this was the state of the art 1 year ago, before we started trying to do that. And what you see on the left axis is the open circuit voltage. On the x-axis here, you see the band gap of different perovskites, and this is just literature data. And the black region here, that's thermodynamically impossible. Yeah, that's above the Shockley-Queisser limit, so no data point is here. That's very good. And then you see here these thin lines that say 1, 10 to the minus 1, 10 to the minus 2, and so on. This is the luminescence quantum efficiency, so always 1 order of magnitude less implies 60 millivolts loss, so KT-ln10 loss in open circuit voltage. So if you take this data point, for instance, then you see it's on a 10 to the minus 2 line, which means it's, in this case, has a luminescence quantum efficiency of approximately 1%. Yeah? And that was the best point at that time here from a paper of Michael Saliba. And you see, in general, there are lots of points, yeah, in the 10 to the minus 3 to 10 to the minus 2 range. Yeah? So that means 0.1 to 1% luminescence quantum efficiency. Okay, and then also roughly 1 year ago, there was this paper by the group from Seattle, David Ginger's group and Hugh Hillhouse's group, on determining the so-called implied open circuit voltage, not of a solar cell, but of a passivated perovskite film. That means they didn't have charge extracting contacts applied to the film, but they did have passivating layers. And then measured the luminescence of these films. And what they found was external quantum efficiencies in these. This is the topo, is a molecule that they used for passivation, that were on the order of 30% external luminescence quantum efficiency, and that would correspond to a quasi-Fermi level splitting of about 1.28 volts with a band gap of 1.6. So that's kind of up here in that region. Yeah? So pretty good numbers. The problem was only that this was not a device. Yeah? So topo is not a conducting molecule, so you can't easily make a solar cell out of this. Okay, and so the task was then obviously to keep the general idea of having these high quality bulk perovskite layers, and then try to find contact layers that allow charge extraction but keep the high quasi-Fermi level splitting. And the highest values that we reached with these typical band gaps of 1.6 electron volts that you get for these methyl ammonium lead iodide perovskites was 1.26. Yeah, so that's 20 millivolts, less than what the Seattle group got without any charge extracting contacts. And the stack that we used was this one. So that's not actually a very uncommon stack. It uses PTAA, that's this polytriarylamine molecule as a whole extracting layer, and then PCBM and BCP as the electron extracting layers. If you want to talk about the recipe for the perovskite, we can discuss this later. This is all published in as much detail as we could, because there are lots of things can kill the process. Yeah, like glove box temperature 2 degrees off, and the process doesn't work anymore. Yeah, we try to write everything down as good as possible so people can try to reproduce it. And I think one of the key aspects of it was that we used a precursor, that's lead acetate, that has been used by some groups but not many, and combine it with contact layers that have been used by some groups, but not many. And just, I think nobody tried this combination. And this combination seems to work quite well for open circuit voltage. Yeah. Okay, so what we have is essentially around 5 to 10% external luminescence quantum efficiency in a working solar cell, which is about 95% of the radiative limit. But if we have a quantum yield, luminescence quantum yield of 10%, it still means that 90% of the photons end up creating some sort of heat. Yeah? So we still have lots of loss processes, so we have probably some bulk recombination via defects. We have some parasitic absorption of photons that are created by radiative recombination inside our device and then are absorbed, for instance, in the contact layers. We have probably some surface recombination, but not much. And the devices at the end then look like this. So one of the challenges we had, so if you remember Elisabeth's data, she had like 22 milliamps per square centimeter. We never managed to get such high short circuit current densities. No, I don't. I think that was perfectly correct what you had, 22 milliamps, but we never got above 20. Yeah, and I think the Schock-Quasar limit for this band gap is 26, 27 or something like that. Yeah, we just can't get higher because the process doesn't like, at the moment, it doesn't like making the device very thick. Then it gets quite rough and not the high open circuit voltage is not there anymore. So this is one of the challenges. Because it's quite thin, we get fill factors that are okay, but they're also not perfect, and the efficiencies are on the order of 20%. Okay, yeah. So here you see we have two processes, A and B was trying to get it a little bit thicker, so you harvest more light here in the near infrared and in the blue. And also we try to make these contact layers as thin as possible to get more photocurrent without compromising the open circuit voltages here. Okay, now one of the motivations for getting high open circuit voltages, apart from just having a high efficiency in a single junction solar cell, was for us to find materials and systems that could be used in tandem cells, for instance, on top of crystalline silicon. Of course, there are lots of practical problems with that, different levels of stability. One material lasts forever, one material doesn't. But from a scientific perspective, it's interesting to look what is possible here. So this graph shows you like a rough calculation of what level of efficiency you could approximately reach in a tandem solar cell on top of that 26.6% silicon solar cell that Pedroca already showed you from Kaneka. And this solar cell has a voltage at the maximum power point that is about 625 millivolt. Yeah? So the open circuit voltage is on the order of, I think, 740. The voltage at the maximum power point is about 630. And so that means if you want to make a tandem solar cell on top of such a high efficiency solar cell, what you need is a short circuit current density of 20 something, 20 and a bit. And you need to have much more voltage at the maximum power point than 630. Yeah? And so most people, they don't tell you what the voltage at the maximum power point is. It's not something that's typically found in papers, except you digitalize the whole current voltage curve. So I used the VOC fill factor product as a proxy for the voltage at the maximum power point, and then tried to calculate the efficiency that you could get. And this point here, that's our data point. So our solar cell with the 1.26 volt is the first halfway efficient perovskite solar cell that got just above the 1 volt threshold for the product of VOC times fill factor, and also for the voltage at the maximum power point. And you see, if you could keep the 20.7 or so short circuit current, if you remove the back reflector, the back mirror, yeah, and then put it on top of a silicon, crystalline silicon solar cell with 26.6% efficiency, you could go towards 34%. Yeah, we tried it, of course, and it totally doesn't work yet. Yeah, because we can't keep the 20 milliamps, not even close. Yeah, and we have lots and lots of technical problems getting there. Yeah, but it's an interesting estimate of where you could go, and by now we've also tried to increase the band gap a bit, add some bromine, and then we can go up with this product to 1.1. But we are down here with the short circuit current, so I didn't even bother to put it in there yet. Yeah. So the higher band gap perovskites, they are not so good yet in our lab. Okay, now let's have a brief look at the losses in this type of solar cell. So what you see two graphs now. On the left, you see power density versus voltage. On the right, you see current density versus voltage. And the blue one is the experimental data for the downsweep, which gives you these numbers here. And the red would be, let's assume the fill factor was Shockley-Queisser limit was perfect. Yeah. And the green is, let's assume the VOC was perfect. Yeah. And the perfect always means Shockley-Queisser limit. For all the other parameters, the same. Okay, now let's first look at this difference. So this is the same VOC, but perfect fill factor. Yeah? Perfect fill factor is defined by 0 series resistance, infinite parallel resistance, and an ideality factor of 1, which maybe you can debate about. Yeah? And you see that there's actually 10% difference. So that's actually quite a lot. Yeah? So there's a lot to gain there, surprisingly much. Although everybody will say 80% fill factor sounds quite all right. Yeah? It's still quite far away from the theoretical limit, much further than crystalline silicon, where you can get to 81, 82% experimentally, and the theoretical limit is 84. Yeah? So there's much less to gain there than here. And we have series resistances that are actually quite horrible for crystalline silicon standards. Yeah, they're like 5, 6, 7 ohm centimeter square. Yeah, they're actually not very good. Okay, then in terms of what is still there in open circuit voltage, so that's 60 millivolts still to gain here. From here to here, that's actually not so much. Yeah, so maybe a little bit, but probably that's quite close to what you can get. Okay, now what are the reasons for these losses and how can we experimentally study these losses? So what I think is that our contact layers are quite good, well suited to suppress non-radiative recombination, but they have some other issues. And we try to study these issues, resistive issues in particular, by doing a simple experiment, namely photoluminescence, but trying to do this relatively simple experiment in a device at short circuit, which is something that you usually don't do. Yeah? Usually you do photoluminescence at open circuit, but let's do it at short circuit and see what happens. Yeah? So what you would expect is, okay, you create electron hole pairs with your laser pulse, you do it steady state, so you create them all the time, and then you short circuit that. So ideally they just go out and through the circuit and are gone. Yeah? So you wouldn't ideally expect to measure lots of luminescence, but you do, unfortunately. So okay, so this graph's now a bit more complicated. So this thing here is an estimate for the quasi-Fermi level splitting as a function of voltage. And it's calculated just by taking KTQ times ln of the photoluminescence. Yeah? And you do that on a device, and the device has a, you connect it to a Keithley and change the voltage. Yeah? And then step by step measure the photoluminescence. And when you do that, you get like quite a lot of luminescence at relatively low voltages. And this luminescence is on the order of, say, 5% of the luminescence you have at open circuit. And that means that your quasi-Fermi level splitting must be really high at short circuit. And I don't know why, or I think it's not good that it's that high. It should be lower. So I think it should be more like this. Yeah? And to do that, I just made these contact layers much more conductive. Yeah, if you make them more conductive, then your quasi-Fermi level splitting in the perovskite will go down quite a lot. And I think that's probably what needs to be done at some point. I only don't know whether that will kill all the other good properties of these materials. So maybe there's some fundamental compromise here. Okay, next question was the open circuit voltage. Now we do the same thing again, but at open circuit. So now we pump it and see what's coming back. And now what we want is as much luminescence as possible. That's always a good sign now. So if we were in the radiative limit, then the external luminescence quantum efficiency would be 1. And if we are not in the radiative limit, then every order of magnitude we are losing in luminescence quantum efficiency will lead to 60 millivolts loss in open circuit voltage. And this loss can be due to surface recombination or due to bulk recombination. Okay, now what we tried to do was try to identify at which interface we are losing open circuit voltage, if any. And this was a method that was nicely introduced in this paper. That's not from me, that's the group in Potsdam. And I'll just use their graphics for illustration to give credit where credit is due. So what they did was to essentially take the perovskite on glass, then the perovskite with one contact layer, so C60 in this case, perovskite with the other contact layer, so the whole extracting layer, PTAA, and the perovskite with 2 contact layers attached. Always measure the photoluminescence at constant laser fluence, and then see how much luminescence I get back. And then from the logarithm of the luminescence, calculate the quasi-Fermi level splitting that you get. Okay, so radiative limit is somewhere here, 1.34 or so. Perovskite on glass was 1.2-ish in their case, and then they lose with one contact, with the other contact, with both contacts, they lose more, and then they get typical open circuit voltages of 1.12 or 1.13 in their devices. Yeah? If we do the same thing, then it's a slightly, in our case, slightly different band gap, therefore slightly different radiative limit. And then we go down to 1.27 and a bit in this completely passivated film. So that's perovskite with topo on top, like in the Nature Photonics paper from the Seattle group. And then we already are with the complete cell is already the next that we get. And there's basically no difference to 1 contact, 2 contact, or the complete cell. Luminescence is basically the same. Yeah? So that's quite different to their study. So there doesn't seem to be any strong loss of open circuit voltage due to the interfaces. And now the question was, okay, can we actually measure something like surface recombination velocities using, this case, transient photoluminescence? That was the next thing we tried to do. And what we did was, okay, measure transient photoluminescence as a function of delay time in 3 different samples. So one was essentially stopping it after the perovskite. So that means there's 1 extracting contact, the whole extracting contact already attached, then having 2 contacts and having the complete cell. And honestly, I think these transients are very complicated and difficult to really interpret because there's so many things happening at the same time. So we only bothered to then look in detail at this, where we have 1 interface and the perovskite that looked like it could be done. And what we did was, essentially we thought we have 2 key reasons why the luminescence is going down. Either it's the bulk or it's this 1 interface that we're having. Yeah? Because we know that perovskite towards nitrogen, which is like the environment in which we did the experiment, that has very low recombination velocities. And what we did in this graph was we assumed that bulk recombination, non-radiative bulk recombination, is very, very slow. Yeah? Like 10 microseconds lifetime. This is like extremely slow. And then have a look at what kind of surface recombination velocity we need to explain our data. Yeah, it's good. And result was it's like something below 10 centimeters per second would fit the data well. If we do the opposite, so this is same graph as before, and this is now assuming that surface recombination is essentially zero, or it's exactly zero, then we see that something like above 3 microseconds bulk lifetime explains the data well. Yeah. So both cases is very, so this is a very small number and this is a very large number for a direct semiconductor. Okay, this is like the end of the experimental part. And now I want to essentially repeat and go a little bit, only a tiny little bit beyond the talk that I gave last year. So the first 2 slides are just essentially a quick reminder of what I did last year. So the idea was to try to understand the reasons for these particularly slow recombination at the bulk and at some interfaces at least in the perovskites, and that's work I did with Tom and David. And so essentially when you calculate, say, Shockley-Rittal recombination rates, that means the rates of recombination of an electron with a hole in a semiconductor, and that recombination goes via some in-gap states, then there's essentially 2 quantities you need to think about to understand. So one is how many of these defects do you have, and then how quick is the transition from band to defect and from defect to band. And okay, how many defects, that's one part of the story. The story I told last year was how can we calculate or at least estimate the value of these prefactors, these kinetic prefactors. So how quick is a transition happening? And that was essentially based on theory that Tom published in 1981 and some theory from Brian Ridley that was published in 1978. And in this paper, we just put in the values, the material parameters we know from these lead-halide perovskites. And this is a graph that's slightly different than the one I've shown last year, hopefully a bit more illustrative. And that tries to just explain how high these transition coefficients, recombination coefficients are as a function of the position of this defect level. Yeah. So essentially this is the conduction band, this is the valence band, the band gap is around 1.6 electron volts. And if you move this up and down, then if you move it closer to the conduction band, then the transition Kn from conduction band to trap will be more efficient. And if you move it down, then it will be the other one that's more efficient. And that is based on the general idea that the more phonons you need for one non-radiative transition, the more unlikely it will become. And if you use the parameters of perovskites, that you see that every transition that is below, say, 400 milli-electron volt for one single jump is fairly efficient, and then it goes down like, you see this axis, it goes down like really, really strongly. Yeah? This is due to number of phonons factorial that's somewhere in the equation. And then if you have it mid-gap, then you see they're nearly equal. Okay. And this is like one part of the story, why the perovskites are seem to be relatively defect intolerant, that tolerant, that the Ks are quite small for mid-gap defects and also small for defects that are not mid-gap. And the second question was then, is there a reason why there are less deep defects in these materials than there are in other inorganic semiconductors? And if you think about normal, like silicon or gallium arsenide semiconductors, then usually the valence band is built up of a bonding orbital, the conduction band of an anti-bonding orbital. And if you take any bond out, yeah, you create a valence or interstitial, then usually you will create relatively deep defects. In the specific case of these lead-halide perovskites, then the lead-halide cage will create both valence and conduction band. And the tricky thing is that now the valence band maximum is made up of antibonding orbitals between the lead-6s and the iodine 5p. And the conduction band is also an antibonding orbital. And if you now take anything out of these bonds here, then you create either states inside the valence band that don't matter really, or very shallow states, and the same is here. So it's not that there are no defects in the perovskites. It seems that the defects are creating lots of shallow states, if any. And the combination of these shallow states with these specific low phonon energy, the low phonon energies and the values of this Kn and Kp then lead to the following situation. So that's the final graph summarizing these things. And this graph tells you what the effective lifetime, Shockley-Rittal lifetime. Yeah? If you take this equation for Shockley-Rittal recombination and try to summarize everything in one effective lifetime. Yeah? And this is the one that's then at the end influencing your open circuit voltage. Yeah? And if you take 10 to the 15 defects and put them anywhere in your semiconductor, yeah, if you take the mid gap, then you would get like on the order of 10 to the minus 6, so hundreds of nanoseconds lifetimes. And if you take them out of mid gap, you very quickly get much longer lifetimes because one of the transitions becomes really slow. Yeah, this is at least what this for a relatively simple theory of one transition only would predict. Yeah, now you can think about what kind of other situations you could have, like more than one defect to defect transitions, and so on. But in this simple case, it would very easily explain why the material is defect tolerant. Okay, now this is a question for Tom that I already announced yesterday in the restaurant. So there's one funny thing is that you might think about is what is the importance of Coulomb attraction? If you have a transition of electron being captured by a positively charged defect and then making it neutral by this capture event, how much is the transition amplified by the Coulomb attraction? So this goes all down to a few papers by some Professor Pessler, and these papers were written in the 1970s, and I have massive difficulties understanding them, but Tom nicely summarized them. And if you take Tom's equation for this Sommerfeld factor, which is summarizing the attractive interactions between the electron, for instance, in the conduction band and the positively charged defect, then you see that the factor with which you have to multiply these transition rates is dependent on the relative permittivity and the effective mass. There's only one problem, is it starts at 1 here, but the equation doesn't end here. Yeah? So according to theory, Coulomb attraction could also make the transition less likely. And that's something that is not, for me, it's not understood. I don't understand how this can be. Yeah? So if you want to have that in theory, you need very low effective masses and very high permittivities. And I don't know what happens then. Yeah? Maybe there needs to be another theory here that makes sure that these lines don't go below 1. Okay, now summary. So we have quite nice open circuit voltages. I'm not saying this is the most stable and industrially upscalable material on the planet. Yeah? It's very oxygen and water sensitive, but if you keep that out, it's relatively stable. Yeah? So it doesn't have much problems with light, for instance, but you have to find a way of encapsulating it extremely well. Okay, so transient PL also shows very long lifetimes, that's fine, but we don't understand yet how to interpret the device PL yet. And these are all the open questions for discussion, so I'll just go through them. So this is one I had last year already. So unharmonicity, how to calculate non-radiative recombination if you are not in the harmonic limit anymore. Surfaces, so this is an interesting question, how to understand theory for non-radiative recombination at surfaces. That's an unsolved problem for me. And then the question of organic contact layers. So these high open circuit voltages were achieved with 2 organic contact layers. This leads to problems, I think, in fill factor, for instance, because they're not very conductive, but it seems to work very well in terms of recombination. Now, why is it working so well? I would say the large energy of vibrational modes in organic semiconductors should actually be a disadvantage for passivation and recombination purposes, but doesn't seem to be a disadvantage. So maybe the electron and hole that are recombining at the interface cannot easily release their energy by just making the polymer wiggle. Yeah, because essentially in organic semiconductors, it should be very easy to release energy, and therefore non-radiative recombination rates are typically high. Yeah, so but apparently that's not the case, and I don't understand why. Okay, then next question. Amphoteric defects, more than one charge state, more than one energy level maybe. There's lots of literature on, for instance, gallium nitride. Yeah? So if you take this theory, apply it to gallium nitride, the result would be no matter how many defects, it's always fantastic. Because just because the band gap is so high. Yeah? And sufficiently high band gap, at some point multiphonon transitions will become infinitely impossible, yeah? Or like infinitely unlikely. But still, it took a Nobel Prize and probably 2 decades of work to get gallium nitride good enough to make a blue laser. Yeah? And there are people that are trying to think about this. But this is also something that is not entirely clear to me, how to explain non-radiative recombination in high bandgap semiconductors. Yeah? Okay, the rest I've already said. So that's like understanding the experiments is still a challenge in some cases. Thank you.